we're set up now. So I'm Kevin Turner. I'm chair of the Department of Mechanical Engineering and Applied Mechanics, and I'm pleased to be here today to host and introduce Professor Michelle Johnson. So Michelle is a tenured associate professor of physical medicine and rehabilitation in the Perelman School of Medicine at the University of Pennsylvania. She's been a MEAM graduate group member and advises MEAM PhD students, as well as a number of MEAM undergraduates and master's students in her lab and research for a number of years. She also holds a secondary appointment in bioengineering in the School of Engineering and Applied Science. So Michelle has a Bachelor's of Science in Mechanical Engineering from the University of Pennsylvania, so from our department. So not only is she a faculty at Penn, but she's an alum of MEAM. And she received her PhD from Stanford University, also in mechanical engineering. Prior to starting her faculty career, she completed an NSF NATO postdoctoral fellowship at the Advanced Robotics Technology and Systems Laboratory at the Scuola Superiore Santa Anna in Italy. She directs the Rehabilitation Robotic Research and Design Laboratory in the Pennsylvania Institute of Rehabilitation Medicine at the University of Pennsylvania. Again, this is in the Perelman School of Medicine. And she also is affiliated with the GRASP Lab, which is at the University of Pennsylvania. So Dr. Johnson's lab specializes in the design, development, and therapeutic use of novel, affordable, intelligent robotic assistants for rehabilitation in high and low resource environments, with an emphasis on using robotics and sensors to quantify upper limb motor function in adults and children with brain injury or at risk for brain injury. So we're pleased to have Michelle here today to give a MEAM seminar. As I said before, she's been involved and engaged in the School of Engineering and in the department for a number of years. And we're pleased to, we look forward to hearing her seminar today entitled Robotics and Mechatronic Systems Can Help Us Identify, Assess, and Treat Motor and Cognitive Impairment After Brain Injury. So thank you for joining us, Michelle, and we look forward to your seminar.
Thank you so much, everyone, for inviting me, and hopefully we'll be able to kind of learn, if people are not familiar with what I do, to kind of understand a bit about what we're focused on. So today I wanted to just talk a little bit about a rationale for kind of why I do what I'm doing, introduce my lab a bit by kind of thinking through what is robotics and some of the projects and collaborations that we have, and then talk a little bit in detail about 2 case studies. So why do we do what we do? I think one of the biggest motivation behind my work is thinking through about the fact that cardiovascular diseases, non-communicable diseases, and a variety of issues are kind of like our biggest health challenges nowadays. And what's important to note is that a lot of these diseases lead to disability and are the major causes of people living with impairment after, for example, high blood pressure, strokes, HIV, dementia, and stroke, and even neonatal and care and those types of issues result in premature births, which then result in cerebral palsy. And what's really true is that there's a growing number of people living with disability and living with impairment after a variety of diseases. And the challenge, though, is that there are a shortage of clinicians and people who are able to take care of this population. And so there's kind of a care gap in healthcare for those that have impairments or struggling with motor and cognitive and a variety of disability. And my philosophy has always been that technology can help bridge this gap. And the technologies that we focus on is kind of thinking through how do robots, therapy robots, can fill this gap. This area began more than 20 years ago, and I would say that I put a picture of the MIT InMotion robot here, and I would say that was one of the earlier systems that began this field of therapy robots. The idea was to work with, for example, someone like a stroke survivor that has neurological impairment after stroke, and to think about ways that we could alleviate the high pressure that's on the clinical environment, and that maybe the robot can function as an intelligent assistant. So the idea is to automate and deliver autonomous or semi-autonomous rehabilitation, repetitive, repeated practice to the arm or the leg, in this case, the locomat, and the idea of being able to use sensing and our capabilities from the technology aspect to assess the level of disability, the level of impairment, and try to then deliver therapy through motion and movement, sound, et cetera, now that it's evolving, to quantify and change the course of that person's function. And then also the goal is to reduce the impairment in some specific manner. When this area began, it was primarily in inpatient hospital type facilities, supervised settings. Now we're kind of evolving to, we're thinking about how do we use these systems in low resource settings, in developing countries, in the community. So then the challenge kind of changes as you go along. Another category of the technology that I leverage is the idea of assistive robots, essentially robotic systems that are being used to replace some type of activity function. I'm not as focused on the prosthetics, even though I'm definitely interested in that area. I would say because of the population that I usually focus on, which is stroke and cerebral palsy, where the patients have an intact limb, maybe the orthosis and those types of systems would be more in my wheelhouse. So this is a nutshell of kind of like the three big areas that my lab is involved in. What we're trying to do is, it's an interdisciplinary team. We use robotics, rehabilitation, neuroscience. The main areas in neurorehabilitation, we think about affordable robots for global health environment and for mobile and therapeutic assistance. One of the biggest things that I do is I work very closely with clinicians, occupational therapists, especially since I focus on the upper extremity, and think through how do we better create robots and these technology tools to assist persons with disability. Some of the key things I think about and that have been happening in this particular field is we first say, well, we want to track and understand the therapist movement. So what does that mean? From understanding the human-to-human interaction, we know the desired trajectory, and then that leads to providing and creating kinematic models. From understanding the interaction force between the human and human, how's the therapist touching the person, how's the therapist lifting, how is the joint being moved, we may then be able to try to understand a bit about force requirements, and then think about the haptics models that we would use in order to support the robot's interaction with the patient. The other piece that, so I've innovated in these areas. One of the pieces that I've recently begun to innovate is in this area of understanding the intent. I feel like a part of our challenge is in this area of rehab robotics is that we're pretty good at kind of this modeling part, but we often lose our understanding of what is actually happening in that human-human interaction with the therapist, or what is the intent of the individual. So one of the recent projects is to begin to understand what's the therapist's role in behavior, and then kind of breaking that down into what are the cueing that's happening both physically and verbally, administratively, so that we can begin to understand intent, with the hope of then being able to build a better human-robot type interaction. Here's an example of some of the activities that we studied, or videos that we looked at. And this actually was in collaboration with a colleague at Temple University, and one of my past master's student who currently now works in Catherine's lab is studying these particular videos, looking at coding them, understanding kind of what is going on in the dynamic. And then we propose this model, this stimulus response model. And the reason why we picked this model is because we wanted to overlay this on any type of robotic system. And we are also thinking about behavioral-based modeling in the way we think about how therapists might interact or how a robot might interact. Well, we discovered that there were kind of three main dyads happening: the therapist as demonstrator, patient as observer, the therapist as helper, the patient as being helped with assistance, the therapist as observer, and the patient as performer. And what we thought was that for the relationship to change and the human-human relationship changes when some cue is occurred. Maybe the person says, okay, I can't do this anymore, or there's a mistake in the way that the patient is doing the behavior, so it's not quite the desired behavior that the therapist would want. And so it causes kind of change in the interaction. What's true is that when we think about how can we automate or aspects of the therapist's activity, we want to then think about, well, can robots take on these three behaviors: demonstrator, observer, helper, to co-act with the patient? So what's good to note is that the helper role, we see that a lot already in the therapy assistive robots that we work with, and I'll show you a couple of videos. And then the demonstrator observer roles we often see in the assistive robots and the service robots that we work with. But what we often don't see is transitioning from the therapy robot to the assistive robot space and back and forth. So that's a part of kind of thinking about innovation in this particular area. So this is an example of a robot system that we use. It's called, we used the haptic master admittance robot. We created an environment we call the activities of daily living environment. And the idea was to program the robot to apply forces in a way that would support someone with upper extremity disability.
Hi there, I am Little Flo, a remotely controlled robot for telerehabilitation, and this is my operator.
So this is sorry, moving ahead a bit. So you've already heard from one of my PhD students, Michael Soberpera, as he had presented in a past recent MEAM seminar on the work where we're looking at demonstrator and observer role and developing this mobile robot system that can be used in a telepresence environment, that can be used remote from the clinician. And we're innovating on kind of affordability as well, thinking about how this humanoid robot can make a difference in therapy environments by focusing on this demonstrator assistive role. This is another demonstrator observer type interactive robot. This was done in collaboration with Dr. Kuchenbecker and her PhD student, who is now a faculty, Dr. Fitter. And here we were looking at the role of a humanoid robot in supporting elder exercise in the demonstrator observer roles. We've also done some work with Mark in kind of a social robot world work here. Mark, I didn't put a video up, so I apologize, but I want to acknowledge that the work that we do with Mark is in this area of a demonstrator observer mobile robot. So one of the things that we've also thought about is how do we transition? So if we use this Baxter system as a template, so the Baxter is observing the patient. So I had a student kind of think through, like, how would we transition from observer to contact to helper? So this observer to helper role. So we thought about, well, if the patient is trying to reach for a cup and we model the error parameters around this movement, can we teach the robot when to intervene? And so this is an idea or an example of the robot notices an error and then supports the patient to get to the cup. So this is, those are kind of like a quick look at the types of work that we're doing in the lab and the types of ideas that we're focused on. So I'm gonna talk specifically about 2 case studies. And in these case studies, we're going to focus on the idea that I presented in terms of the talk, in terms of understanding and the use of robot systems and mechatronic systems to help actually a specific type of user and to support the assessment of the user as well as motor intervention. So I'm going to focus on first case is work done by my PhD student who's in bioengineering. And the idea of here is, how do we use robots to help assess a population, and for us, a new population, people with stroke and people with HIV. So because it's a technical talk, I want to first place everyone within the context of what's happening with stroke so that I don't make any assumptions about what people know about the disability. So stroke is actually the leading cause of adult disability in the United States. There are over 4.5 million stroke survivors. Every year, about 700,000 people are getting a stroke, and most of these strokes are new strokes. 75% of stroke survivors will end up with what we call hemiparesis. And this is a great pick. I always like to show this pick in terms of, this is a very severely impaired person with stroke who is now dealing with an upper extremity that might be in more of a flexor synergy, so they can't independently move their limb, they can't independently move their elbow, and they're also dealing with gait issues due to a lower limb that might be more in an extensor synergy. So they may end up having some gait challenges as well. So we're going to focus now on kind of the upper extremity. And so thinking about, how do we assess motor function, and how do we use robot tools to understand the impairment level of this upper extremity, as well as you saw the Adler as we were trying to move. That's the idea of, how do we use robots to actually intervene with the upper extremity to cause change in functional levels. So this is just a list of a lot of the robot therapy protocols that have been out there that have been shown actually pretty strong evidence that robot assisted therapy can actually be a legitimate way to support people with stroke throughout in terms of their movements and recovering their movements. One of the things that my student and I were really trying to look at was, is there a way to use these, to use robots to not just look at motor difficulty or assess motor difficulty, but also assess cognitive issues. And one of the things that we found is that majority of the studies out there on robot assisted therapy are focused only on the motor activity and not on the cognitive level of the patient, and how cognitive impairment might actually mask movement. So we started kind of like branching out and trying to expand the application of robotic assisted therapy to patients beyond just those with motor issues, but trying to support patients with cognitive issues as well. So this was just like some data that showed that 43% of stroke survivors will have cognitive disability, as well as the motor disability in the upper extremity. And that even as much as 3 years out, 30% of them have a mild cognitive impairment. So this just justifies that thinking about how robot assisted therapy can expand beyond people with motor issues is an important thing if we want to be more inclusive of the types of people that we support using rehabilitation robots. So this is kind of a pick that we came up with to think about what and the impact of robot assisted therapy on the sequelae of someone with, for example, stroke. So usually after a stroke, about 6 months is the chronic phase, just to situate everyone to this graph here on the x-axis. So clearly intervening with robotics early within the 0 to 6 months can actually increase the rate of recovery. If we say on the y-axis is the scale for motor recovery in the upper extremity, can actually improve that. What happens though, if you're cognitively sound, the improvement that we expect, even without robot assistance, is going to be a lot higher. However, if you're cognitively impaired, that improvement is lower. And so one of the things that we're hoping to do is, one, we want to use the robot assisted therapy here in the acute phase, but also in the chronic phase, that we already see by data showing that with the robot assisted therapy, we can push recovery of those that are chronically sound and to improve their recovery. but not many people have looked at for those that also have impairment. So, so our goal is to apply robot-assisted therapy, not just to those that are chronically sound, but also those that are impaired. It was a challenge to work with people with impairment, but one of our reasons for also including HIV, and HIV, as you know, is a communicable disease that was really rampant in our society and our world. You know, 30 years ago, people were dying massively from it, kind of almost like the COVID back in the it could have been considered the COVID in the 90s, but currently now there's about 1.2 million people and 36.7 million people worldwide living with HIV. Something that's little known about HIV is that HIV actually is a risk factor for stroke. And that's something that's been recently formulated. And the reason we got into HIV is because our work extends beyond the borders of the US. And we started working with colleagues in Botswana, where the people who presented with stroke also presented with HIV. And where in the brain that there is an issue with HIV, it's not just in the motor areas of the brain, but we see that HIV will cross the brain barrier and affect the frontal temporal lobes of the individual. And so we find that there are different areas that might be affected, i.e. one of the biggest issues in HIV is what they call HIV-associated neurocognitive disorders, which result in some cognitive issues, but also some motor issues as well. So because we were looking to work with our colleagues in Botswana in terms of affordable rehab, my student took on this challenge of kind of trying to transition our stroke work to people with cognitive issues, but also using HIV as well as a model for what we wanted to do. This just kind of talks a little bit about the fact that the incidence of stroke amongst persons with HIV is actually increasing, and we see that in the United States as well. And this is actually probably also related to the fact that people with HIV are now living longer and they're surviving into chronic age. So thinking about their living and their quality of life is something that we're wanting to do because of our work in Botswana as well. So this is something that just a kind of a way of thinking about how we're putting together stroke and HIV and people with cognitive issues and those without. So one of our strategies is to say that if we're going to use robotics, we need to figure out where and how to apply it. In this particular group up here, where the person has high motor function, they have a lot more ability in their upper extremity, and then there are very little cognitive issues. These are the people that we probably don't do a lot for in the robotics. If they're over here in terms of moderate motor function, we know that we can intervene with robots and that we can make a difference. When we think about low motor function and high cog, this is the group that we actually do a lot more robotics with, and that there are solutions already out there for. But this group here with lower motor function and high motor function and lower cog, this is the group that we're trying to incorporate within our robotics. So we feel that we and the work that we're doing can make a real difference in terms of applying robotic techniques and neurorehabilitation strategies to this, to include this particular group in the people that we can reach with our robotics. So the reach goal was to think about, first, we need to be able to quantify on the fly motor and cognitive issues. And so we need to develop some robot-based metrics that could be able to do this. And then if we can do that and stratify individuals according to their motor and cognitive impairment, then what our goal then would be to come up and innovate with kinematic movement strategies, with force feedback strategies, with control strategies that we can apply to the robot to support people in, as I say, in these different areas.
Michelle, if you don't mind, one question. This is Prashant Purohit.
Sure.
So this question is about why HIV causes impairment in function. And it's this. Does HIV increase susceptibility to stroke?
Yes.
Or does it cross the blood-brain barrier and destroy neurons in the brain?
Actually, it's both. So what they've found in the colleagues that we work with that are the focus on the HIV scenario, see that if the virus, when it crosses the blood-brain barrier, is actually affecting the brain and actually destroying some areas in the brain. And primarily what they've seen is a lot of more frontal lobe type interaction. How it affects there is still work being done to figure out how the HIV virus actually causing affection, challenges to the motor system. What they primarily have seen is fine motor issues as a result, and so as people become more impaired, they've seen disruption in their motor activity as well. And one of the things that we realize is that there is a really tight coupling between motor and cognitive issues. Most activities of daily living require some level of cognitive ability as well. So the HIV virus is shown to definitively affect motor, fine motor. And then one of the things that we're seeing, and we're writing up this paper right now with my PhD student, is that it also affects gross motor function as well. So it's killing brain, they call it CNS complication or associated CNS disorders. And then it also can lead to even a massive stroke because of cardiovascular issues as well. Hopefully that, Prashant, that answered your question.
Yes, at least to some distance. Thanks, Michelle.
Okay, so one of the things that we're trying to do, and whenever you're working in rehabilitation robotics, a lot of the challenge to the clinician is that, well, how do we know this works? And given where we are in terms of our clinical activities, how can you prove that robotics tools are really able to make a difference? So we always have to confront the robotic metrics that we do with actual clinical metrics that are out there that are considered standard, that they're using in the hospital environment. So these are the list of 4 key ones that we used in this particular study that's been used in the hospital environment to assess motor function. And these are the 4 key ones, actually 5 of them, because color trails 1 and 2 are 2 different things, that have been used for cognitive assessment in the clinical environment as well. So what we have to do is prove that any robot-based metrics that we develop can actually correlate to these clinical tools. And one of the things that we know is that if we can prove correlation and we can prove that these are our processes are objective, then we actually have stronger tools than what would be evidence now in the clinical area. So the system that we built is called the TheraDrive system. It's a simple haptic degree, robot here. It essentially, there's a force sensor in the handle, so we understand how the person is interacting with the robot. And the idea here, and we deliberately chose a 1 degree of freedom system because we want to map this system to our colleagues in the low resource environment of Botswana. So this is the example of the tracking task. The idea here that the person has to do preview tracking and they have to keep their icon and the robot tracking this particular idea. And then there are several different metrics that have been used with that. Here's an example of the results of tracking someone with HIV and then someone with HIV and stroke. And you can see that the person with HIV has a little bit better functioning in terms of the errors that they make, and that you can see that sorry, I misspoke. The dashed dots here are the desired. The person here with HIV and stroke is actually higher functioning than the person that just only had the HIV in this instant. So just an example of what we kind of see with the raw data. Then my student actually developed, there are two metrics that we wanted to incorporate and see if we can create into robot-based metrics. This particular metric is the idea of just looking at working memory. It's called the NVAC task. And all this is actually a simple fix. It was just putting a button to allow us to collect reaction time as people, you know, see this particular task. So if it's a zero back task, they're asked to say the number 2 press, then that's the zero back. So you see that. If it's a one back task, it's, oh, you press it if you saw the previous number was the number that you saw, etc. So this allowed us to just quantify reaction time. Very simple fix, but to tie reaction time to cognitive impairment. So one of the key things, I'm just going to draw your eyes down to here. The idea is we actually have them to do this with the non-dominant hand and their impaired, their unimpaired arm and their impaired arm. And what you see is zero back is pretty easy for everyone. The cognitive load is the same, but as you get more cognitively intense, we begin to see differences amongst the healthy group of people and our population affected with HIV and stroke. My student actually now is writing up this paper. He's now had 21 persons with HIV and a subset of them having stroke, and kind of being able to now take these results and expound them and have actually definitive conclusion about the ability of the NVAC task to quantify cognitive impairment in HIV and stroke. We also implemented this spatial span task, and the idea was this is a common clinical tool for looking at visual, spatial, and working and memory together. And so the idea here is that a task that required you to move the robot, so that's the motor component, along with the cognitive component that required you to recognize, so you've shown a sequence and then you have to move the robot to capture the sequence. And now we can put a mean sequence length, the number of sequences that you get right, and a performance metric on top of kinematic metrics as well. So this is an example of what the data would look like. And what you could see is, for example, in the HIV group, you see that they can manage shorter sequence lengths than the healthy population. So this actually, what been shown is that mean sequence length now is a quantifiable metric for detecting motor and cognitive function together. So with these, one of the ideas that we mentioned is being able to stratify the patient population. And so finding the right tools to stratify the people in the groups that we mentioned before is something that my students been working on. And if we can do this successfully with the type of metrics that you just saw, then we can tune our intervention strategies appropriately. So that's kind of where we're going there. As you can see that, for example, this is one chart of saying, were we able to predict the clinical score of the box and block using our robotics metric? And the answer is yes. And that some of our metrics we've actually identified conclusively robotic metrics that do a really great job, a strong to moderate correlation with the clinical scores, both cognitive clinical scores and motor clinical scores. And so for us, the exciting part of this work is that we're now able to say, you could sit down at our robot, do these assessment tests, we can then categorize you, and then we can apply the appropriate intervention strategy for the robot. Any questions on that? Okay, so I'm going to move into just the second case as an example of what our lab's doing in terms of assessing behavior that is both a motor and a cognitive area. This is a work that when we began this work, I began this work actually with colleagues at CHOP, and my colleague, Dr. Cording in BE as well. So when we began, we were just working with CHOP. And the idea here was infants are at risk. There are 50 million premature births each year. Neurodevelopment disorders is affecting a large percentage of children. 2.11 per 1,000 live births is cerebral palsy. This is also higher in lower and middle income countries and amongst people of color. And we wanted to see if we can use our technology tools and mechatronic tools to try to, if we can find these, identify these kids early, if we can apply objective measures early, and we can be more sensitive to small delays might happen as a result of growing old between 0 and 1 year old, then we can make a difference in terms of the sequelae and the outcomes of these infants in the longer run. So we started out with kind of trying to develop what I call our play and neurodevelopment assessment, Jim. And the idea is it's from an engineering standpoint, it's relatively straightforward. It's a massive force sensing mat with mechatronic toys. These were our first iteration of toys. We had actually many of them, 3 of them. Each toy had accelerometers. It had, I think I have a close-up of the toy. We had toys that could encourage kids to open and close, to squeeze. There's a pressure sensor here. There is the accelerometer. So if the kid kicks the toy, holds the toy, hits it, bats it, etc., we would be able to gather that information. So this is just a close-up of like our first iteration of the toy, inertial sensors. There was a grass sensor here. And so this is ways that we can encourage kids to interact with the system. One thing to note is that the system, we also had cameras placed above the system and to the side so that we can collect video data of what was happening. So this is just an example of as the child is moving on the mat, then we're also able to resolve the center of pressure and use that also as a possible metric to understand what's going on with the infants. So this is the mat configuration here. And then as the baby moves on the mat, we're collecting that information, and with the hope that the center of pressure is also a metric that we can use to assess and determine differences between typical kids and atypical kids. I'm going to focus on one research goal that we had. So the idea was, if we can identify these metrics that are able to distinguish at-risk infants from those that are typically developing when they play alone, and then later when they play with toys, this would be awesome from our perspective, because here is a tangible way that technology can support the identification early of infants with potential risk for motor, neuro, and neurodevelopmental delays, as well as cognitive issues, and then we can intervene with them quickly. So one of the goals was, in collaboration, was to think about machine learning techniques to try to automate the stratification of these particular kids. So our first pass was to think big data. And we wanted to gather a database of normative infants and a database of clinical infants. And the goal was, as a first pass of an algorithm, can we create an algorithm that will compare and assess risk? So this is in collaboration with our colleagues at the CHOP, as well as Dr. Corden's lab. And if you're interested in this paper, there's a preprint that's on BioRviz, but we just got the paper accepted in transaction of neuro systems and rehab engineering, if you're interested in learning more. So how do we start? We wanted to curate the normative data set. So we actually went to the internet. YouTube is wonderful for collecting great videos. So we queried 1, 2, 3, 4, 5, 6 months old. We found good and bad videos, of course, but we had to sort through the videos to look at those that were non-occluded. The kids had to be moving independently. Their body had to be present in the video, and we had to actually have enough video to be able to do this analysis. We found a ton of videos, 385, and then we were able to then process the video, to get the clinical data set, we used, we gathered information from the kids in the gym, and the kids actually used, we gathered sets of data. First, the infant was playing by him or herself, and the inclusion criteria was that they couldn't walk, they couldn't have other type of neurological issues except for like the basics that they were premature. We got parents' consent. They did no toy and a toy condition. So they always had one toy at a time. And typically the mean duration was about 200 seconds of video data that we also captured as well. Keep in mind that while we're capturing video, we're also collecting the COP data from the mat. And then whenever the toy was involved, we're also collecting information about the toy as well. So in the end, after we've kind of cleaned the data, we ended up using about, we had about 103 YouTube infants. We couldn't use all the videos we found, but we needed to have our clinical colleagues tell us about the age of the baby. So they were able to, give us kind of usable about 103 videos. And then we finally included 85 of them in our initial analysis. We ended up with 19 babies that we tested in the clinical environment, and we used the clinical metric, it's called Bailey's Infant Neurodevelopment Screener, to try to assess the function of the baby. So we had a priori knowledge that we had 5 babies that were low risk, 9 moderate, and 5 at high risk for cerebral palsy. And the question that was asked is, could we then use an ML technique to try to classify the baby? We started with the no toy condition because the toy condition added an additional issue in terms of a lot more occlusion going on. And so just a lot more challenging. So we're going to start with, we started with the no toy condition so that we can process it, come up with an initial algorithm, and then maybe go back to the toy condition later. Here's the pipeline that we essentially used. We talked about collecting the normative data, the clinical data, the annotating the videos. Then we used OpenPose, which many of you are already familiar with from CMU. The challenge with OpenPose is initially trained on adult data, so we had to actually retrain it on the infants. And then once we successfully retrained it, we were then able to run the OpenPose algorithm, extract the kinematic information, and then we used the Bayes surprise machine learning algorithm to try to classify the baby. Just a little bit more detail, if you're not familiar, the vision-based OpenPose estimation was what was used. It comes out of Carnegie Mellon, using convolution neural networks, heat maps, and part affinity fields to basically try to identify each individual that's in the scene. For us, the scene usually just had the baby itself. OpenPose primarily is trained on adults, so we are one of the first groups to retrain the system on infants. In the retraining, this was the process that was used. Essentially, the process required us to do labeling. We had all our group kind of labeling videos so that we can do the retraining. At the end of the day, we were able to get the error down enough where we felt that we could go ahead and run it with the babies. Here is the video of one of the videos with the OpenPose algorithm on the infant. So cleaning the infant pose raw data, as if you're familiar, is something that we particularly did, removed outliers, smoothed, and because we didn't know where especially for the YouTube data, we didn't know where like the camera was placed, etc. We tried to normalize the videos by the trunk, the length of the trunk, so that we could feel confident about using the kinematic information. We pre-registered the algorithm, got a variety of features that we were interested in and feeling that they would be sensitive to differences between the atypical kids and the typical kids. And here's just a list: position, angle, velocity, etc. And we were particularly interested in what's going on with the hands and what's going on with the legs. Ideally, we wanted to look at the head and the trunk, but because we needed to normalize with the trunk, we're going to ignore, in terms of the OpenPose data set, we're kind of ignoring what the trunk did and we're ignoring what the head did. And we're going to focus on what the arms did and what the legs did. So this is kind of a pass at what some of the metrics look like, just kind of, and the data from the data set. The gray data is the data from the YouTube kids that were used. The green is the low risk kids, the blue is the moderate risk, and the red is the high risk. So here's ankle velocity, wrist. You can see that some metrics, maybe there is a suggestion that there is difference between the at-risk, the clinical group, from the normative group, the healthy group, the typical developing kids. But it's kind of hard to see just from, you know, visually, and using kind of a non-ML type method. So with using the naive Bayesian surprise metric, our goal was to see if, as a first place, could this classify the infants in those three sections. So our initial result showed that we can actually separate out with significant difference the high risk group from the low risk infants. However, from the low risk and the YouTube infants. But the moderate risk group, which is an important group that we really want to be able to separate out, we weren't able to do that with significant difference. This suggests that it's a good starting place, our algorithm, but we might need to look and see and try to, this might be a numbers issue, but it also could just mean a feature issue that we need to gather additional data and look at that. So there are two places we're going with the ML, is gathering additional data. We currently have an R01 to collect 1,200 data points of kids in these different kids that are healthy, kids that are at risk in different ways. And then from that, we can hopefully perfect our algorithm for a classification as well. One of the things is working with the toy. We're really interested in how voluntary movement might be affected by when the toy is present, and when there is when we introduce the toy to the kids in terms of their reaching and grasping, or to them in terms of their kicking motion, how we can induce and look at this voluntary activity as a way of also separating out the atypical kid from the typical kid. So I actually had a student kind of working on coding the different behaviors, and with the ultimate goal of creating some type of ML algorithm that would allow us to be able to understand the data in terms of the toys. So we were primarily focused on classifying movement in terms of involuntary movement, gaze, mouth, touch, kiss, grasp. These are the different types of actions that we observe that babies are doing. Actually, I want to make a plug for, if any one of you, or I know some of you who are like focused in machine learning, if you want to collaborate on this, is like a really good way of extracting this type of information automatically, please touch base. So these are types of interactions that we observe. Gaze interactions with the toy. So you could see the baby looking at the toy. We see the hand engagement. This is another example of the type of toy engagement that we saw for the different toys as well. And then we also saw kicking, you know, them using their hands and their legs, using their legs alone to interact with the toy. So can we, how do we separate these out automatically from the data set that we get? And then for this is one of our our premature kids. This is an involuntary kick. The baby wasn't looking at the toy. just the foot happened to touch. So we'd want to separate that out from voluntary movement of grabbing the as well. The coding was a massive undertaking in terms of coding manually. And that's actually one of the things we want to do is how do we classify these things automatically? What is, for example, indicated is that there seems to be, this is the orange here is atypical kids and the green is typical. There's definitely, just from the coding data, show that typically development kids actually interact with the toy more. They have much more interaction, total interaction time than atypical kids. So this is clearly a feature that could be used to separate out the atypical babies. But this coding process, while we're writing it up and it was manual, it is not the way to go permanently. So this is where using better machine learning could possibly help us to be able to automatically separate out these infants as well. Our next, so we have an R01 that we got last year to kind of look at these issues. And so we're one of the things we realized is the 3 toys were onerous. So we decided to develop one toy that could be both a kick toy and a hand grasping toy that had all the features of the 3 toys that we used before. So kind of moving from this to this ALU. So we actually have a prototype already, a mechatronic kind of toy that allows the face, you can touch the ears. There is a grasp sensor in the hands that allows you to squeeze the toy. There's feedback in terms of neopixels and lights, and as well as sound in the system. We've moved away from this design. This was our first prototype. We're now at like a second prototype where we've PCB a lot of these boards so that the system is a little bit more robust, so that when we go out and we start actually doing work with this particular toy, it would stand the test of 200 babies interacting with it, which they can be very rough on toys for sure. This is just an example of just the baby looking at the toy. This baby is probably about 2 months old. And the younger you are, the less likely you might use your hands. You may end up being more likely to use your legs. But we want to kind of see, does the toy cause the baby to do more? And that's a part of the issue, what we're trying to do. We also move away from our very large system that was not very portable to creating, this is our first prototype where we're trying to test out this idea of a smaller form factor for our system that could be totally foldable, put in like a crate, like a roller bag, etc., and be able to then be taken to infants' homes, taken to daycare centers and other places so that we can collect the data. So this is our initial concept here. And once we finalize this, then we'll go to kind of making it prettier. So I'm gonna stop there so that we have time for questions. Of course, none of this stuff can happen without a lot of people's participation and support, and of course, acknowledging grants that have supported this effort. I'll stop there.
Thank you, Michelle. Thank you for the fantastic talk. So we have some time for questions. As we've been doing all along in these Zoom seminars, please try to raise your hand or note in the chat. I think I saw Rob's real hand up, not virtual hand. So Rob, why don't you lead us off?
Thanks, and I apologize. First of all, thanks for a lovely talk, a very nice talk, and very nice to see all of this interactions between mechanical engineering and medicine and people, real people, benefiting from the technology and the research. And I apologize, I have to drop off shortly because I'm about to teach at noon. But I had just a practical question, I guess, about in translating these technologies into the clinic. What regulatory issues come up? And I'm wondering, in particular, does the fact that you're integrating, robotics into this kind of alleviate or maybe complicate kind of getting past regulatory hurdles? Is that something you have to wrestle with, or maybe your clinicians wrestle with?
Really, really great question. So when they're doing the IRB in terms of our devices, we run into higher regulatory standards when it becomes a medical device. And the medical device criteria is if you are being more invasive, you're changing the patient in some way. So our current robotic systems are not considered medical devices because while the way we're using them right now, because we're using them as assessment tools, they're not considered medical devices. But when we begin to use them to intervene and to change the person's function, then they cross into this regulatory space. And in the IRB, that requires then another level of oversight, what they call it, whenever you're doing the clinical trials, et cetera. So we've been able to avoid some of the regulatory challenges because we stay at the edge of being assessment tools, the developing tools. They're non-invasive, they are not, they're interacting in very superficial ways. They're touching the patient. And so most of our devices in the lab are just considered non-medical devices, so we don't have to jump through a lot of hurdles. However, that's the biggest hurdle, is once it's considered this medical device, is the Office of Clinical Research. There's a whole bunch of other levels that you have to do the testing to translate it realistically into the clinic. Is another level of testing and proof in terms of clinical trial and validation that one, it's not only feasible, but two, you can actually get out in the community, and you need to collect more data than what you've seen here. Most of what we're doing is showing feasibility, and because our differences that we can show are pretty powerful, we feel confident that these things would translate, but we're not even touching the total translation, transfer of the technology part yet. We hope to, as we kind of get more and more data and gather more and more evidence, then we can kind of go after spinning it out of the clinic into the real world.
I see. Great. Thank you.
Welcome.
Other questions? So I had one, Michelle, when looking at the rehabilitation robotics, sort of the earlier part of the talk, it looked like there were a lot of very traditional sort of hard robotic systems. And you hear a lot in the robotics community about soft robotics as being a potential interesting way to interact with people, perhaps, safer, more gentle, because of the additional compliance. And I'm curious what your view is on the sort of future of rehabilitation robotics and sort of hard or more traditional sort of rigid or hard robotics versus soft robotics, and if you see opportunities or if the current systems are more than adequate.
I would say I see opportunities. But I think the soft robotics has big, I think in the last, 10 years or so, that the idea of soft robotics have grown. And I definitely see it having a place in terms of possibly making things a bit cheaper, possibly getting things to be more wearable in terms of orthotics and exoskeletals, et cetera. And I've actually begun to explore some of the soft robotics, but I would say that the questions I'm asking may not necessarily lend itself to kind of the innovation in the soft robotic space right now. But I think there's a huge need for that. Some of the challenges with the soft robotics, I think, needs to be in the actuation space. For me, I like to think about how do we support persons with impairments across the level of functioning. So right now, a lot of the soft robotics are pretty much applied to people with mild impairments and not people with very severe impairments. And so, so I think until there's like some really innovation in the actuation space, where you can really help move and work with people with a lot higher severe disability, I think that's where the opportunity is. I see it being more applied in the mild, moderate, everyday function, which is important because people need to be able to go on with their everyday life, even if they have mild impairment. I think my preference for hard robotics right now is that I want to work with this tougher environment, these tougher groups, and we and for me right now, the actuator space is there for the group that I want to work with that have severe impairment that actually needs motion and movement at this time. But I see this as I think, a huge space, and the work that anyone's doing in that area. I would love to collaborate if someone's interested in, kind of pursuing the soft robotics space within the rehab area, because I do think that is huge, a huge area.
Thank you. Other questions? Oh,
Hi, Dr. Johnson.
Yes. Thank you, Leora.
I was really great to hear from you and see all the work that the lab has been working on since I last saw it a couple of years ago. I have a question from you that kind of piggybacks off of what Dr. Turner was saying. In the lab, there's a lot of focus on providing rehabilitation in like a setting where you would have a robot and a patient. I'm curious if you think that there is room for design of like household products that, say, a child with cerebral palsy would be able to better train themselves to do a specific daily task, and have that be like a one-time purchase that a family would make to improve independency. And I'm curious if you think there's opportunity there, what kinds of tasks or areas you would recommend looking into.
Great question. So yes, I believe that there is room for that. And I think it's actually even more important in some sense than just thinking about functioning in the hospital environment, because majority of what's happening with kids with CP is happening in their classroom, in their home environment. And the types of toys, it's amazing that, yes, there are lots of interesting toys out there, but not many of them, I think we can capitalize on the robotic space in nature to make these toys more able to kind of push the kids with neurological impairments or motor impairments far. So for example, a group in the past, colleagues of mine in Italy worked at trying to think about inquisitive AI toy, robotic toy that would look at supporting kind of gross grasping and fine grasping. And so that the child if the parent would purchase a toy like that, then it's definitely specific to looking at grasping function and supporting that. So I think the challenge has always been cost. Getting into the home environment requires really us thinking about cost. That's something that I care about. I've been, pushing how can we use robotics in low resource settings, and so how do we innovate on cost issues. So that's a thing. I think that's one of the challenges, is getting robotics affordable enough so that if you take the appliance mentality, Leora, where you're saying, I want to buy 4 or 5 different things, right, that a parent can afford, and they are smart AI technology or robotic technology, they're affordable, and they're targeted at my 1-year-old trying to get to the milestone, or at my 5-year-old trying to get to the next milestone. I think there's a huge need for that. There are barriers though, and I think that's an opportunity area, is how do we meld the cost effectiveness with the robotic opportunities that we can provide, Hopefully that helps you.
Yeah, thank you.
Okay, great. So we have a few more minutes. We actually have 2 questions in the queue. I think these will be our last 2 questions. The next one is from Anna Estep.
Hi, Dr. Johnson. Thank you for your talk. So my question is the end goal of the Panda Gym to be used mainly in like a clinical setting to observe these at-risk infants for like short periods of time and kind of check up on them over time, or to be used more in like a daily at-home setting, collecting data like constantly?
Great question. So we've actually explored both. So when our ultimate goal was to think about something portable that could be used in the average pediatric clinic or by a parent. Maybe they could, if we think about a business model or something like that, they could purchase something like this, or they would rent something like this from their clinic, and we would use it to observe over time, a 6-month period, the milestone of the baby and what's happening there. So that's actually our ideal idea. And that also that this system could be leveraged by community-based areas or community-based centers that want to provide some objective way for parents to monitor their growing child for 0 to 6 months. So it actually, for us, our vision is both, but the challenges that I kind of hinted at is how do we consistently get good algorithms that allow us to separate the two, atypical from typical kids. One of the thoughts from our R01, and we pose this in the R01, is, do we need the mechatronic gym? Do we need the force sensing math? Can we get away with just a visual tool that would allow us to do this type of classification? And so, in fact, that's one reason why we're pursuing both sides. We're pursuing where the gym exists, we're collecting the data in kind of this way, and we're believing that maybe the force information that we get, plus the toy, plus all these things, help us discriminate better. However, one thought that we have is maybe we don't need all that, and maybe visual alone can allow us to discriminate. So we're actually pushing both balls down the road, and if we're working with a colleague to use a mobile app to be able for parents to be able to download the app and upload to us 1-minute, 2-minute videos of their infants between 0 and 6 months. And so by gathering that data, we're going to try to see if maybe we don't need the toy, maybe we don't need the force sensing map, maybe we don't need all of that stuff. Maybe all we need is visual information of the right age. So it's a great question. We're trying to figure that out. Our hope is both, but if we get away with just the app, that would actually be, to me, more transforming, because this is something that could be used all over the world and they wouldn't require a lot more money to do it.
Okay, great. So I want to try to squeeze in one last quick question. We're almost at the end of the hour, but Vipit.
Hey, Dr. Johnson, thanks for the talk.
You're welcome.
So my question is, your neurological assessment of babies project is pretty fascinating, and I could see how it would be immensely useful if you could identify these at-risk babies earlier than these labels are currently being diagnosed. So my question has to do with, how are you getting those labels for if a baby is at risk? And would this GYM method be a superior replacement for that process that might be able to catch it earlier?
Great question. So there's a measurement called the gross motor assessment that's done by clinicians. It's a process that requires clinicians a lot of hours of training to do. And in that, they're able to then watch these videos, those that are trained in the process, and classify the infants. And it's usually a time intensive, and you need to be well trained. And so that method exists. With our clinical colleagues, they're like, that's a luxury. That method is a luxury for most clinical areas, and because it takes so much time to get really good at it. So the idea then is, if this system could get just as good at that process without the training required, and without the time required, and in less of, in a shorter period of time, we would then be able to surpass what exists now. So we can't say that we've done that yet. However, that's what we're working towards, because the current system requires high, intense training and lots of time, and it's still somewhat subjective. There's someone there, watching this video and saying, counting fidgety movements and counting this. So can we do this? Can we find features that allows us to do this faster? If we could, then that would really save a lot of time and allow a lot of people to be able to do and apply these techniques. So that's the goal. The current method works, but it's time and money, and our goal is to kind of reduce time and money. I guess it would be a good way to think of that.
Okay, fantastic. So thank you again, Michelle. Fantastic talk. Thank you to all the students also for participating. Great questions today. And we look forward to future interactions with you.
All right, thank you guys.
Okay. Bye, everyone.
Thank you.